So, in our last class we were looking into negative numbers and we have seen that they can be represented either in sign magnitude format or 1's complement format or 2's complement format. Now, how to get back the number, like once it is a negative number and represented in 1's complement, how do we know what is the number? So, it is like this for 1's complement system. So, you can say it is so we define the function f x to be 2 power n minus 1 minus x, then f of f x is x. So, that is if you apply this particular function on itself, okay, so you will get back the x. So, why? Because if we are trying to find this f of f x, then f x is 2 power n minus 1 minus x. So, we put it here. Now, f of 2 power n minus 1 minus x is equal to 2 power n minus 1 minus this whole term. So, it is 2 power n minus 1 minus 2 power n minus 1 minus x. So, this 2 power n and 1 they will cancel out, what remains is the x. So, if you this is the 1's complement representation of the number minus x. So, from there if you want to get back what is the original x, so you can apply the function on it and get back x. So, if you apply on this f, okay, if you apply on apply the function f on this input, so you will get back the original number, okay, so whose negative is actually represented by this representation. Similarly, in the 2's complement case also, suppose so this is the formula for getting the 2's complement of a number. So, g x is 2 power n minus x. So, we have a similar theorem which says that g of g x is equal to x. That is, if you apply the function g on the result g x, so you will get back x. So, as a proof you can see that g of g x is equal to g of, so g x is 2 power n minus x. So, we put it here. So, g of 2 power n minus x, and by this logic that g x is 2 power n minus x. So, we can write that g of 2 power n minus x equal to 2 power n minus again 2 power n minus x, because this x at the place of this x we have to put 2 power n minus x. So, we put it here. So, this way we get this one. So, we get back the x. That means, both in 1's complement and 2's complement notation, if you want to get back the original number whose negative was represented as 2 power n minus 1 minus x or 2 power n minus x in 1's complement or 2's complement, to get back x. So, you take the 1's complement or 2's complement of the number. So, you will get back the original number x. So, it is helpful for our understanding. Okay. So, if you are getting a negative number, so what was the original positive number? So, you can get back by applying the function again. So, next we will see the representation for floating point numbers. So far we have considered only integers, positive and negative, and we have also considered fractions, like say we have seen that these numbers where the number of digits that we are using for representing it is fixed. So, like you can say we have representation like say 15.53. So, we have seen that this 15 part we are converting it into some integer part, then this point is there, and then this 53 also we are converting to binary to represent it. So, that way this representation problem comes when this number of bits that are allocated for this part and number of bits that are allocated for this part, they are same, they are fixed. Okay. So, you cannot change them. So, like if I say that, so for example, for representing 15 you will need at least 4 bits, and for representing 53 properly, so you will be again requiring say, suppose I give you say 5 bits. So, 5 plus 4 total 9 bits are available, but 9 bits are needed. But in reality, so if we give you say only say 5 bits, then for the sake of accuracy, how do you choose, like how many bits we can give for this integer part and how many bits we can give for the fractional part. So, if you are using this real number representation in the form of fixed point notation, so there are problems in terms of accuracy. So, we will see that we can do better by realizing them in the floating point form. So, we will be looking into this floating point representation in the next few slides. So, these real numbers. So, 2's complement numbers that we have discussed so far, they deal only with signed integer values, and without modification these formats are not suitable in scientific or business applications that deal with real number values because of the accuracy and all. So, floating point representation, they will solve this problem. So, we will see that this floating point representation, so they can help us in having better accuracy and all. So, if in fact, before going into this discussion on this floating point representation, one thing we should keep in mind, that ultimately this floating point is representation is nothing but collection of some integers. Okay. It is every floating point number is represented by means of a collection of integers. So, if in the programming we can use some tricks by which we can do these floating point operations ourselves. So, if underlying machine or say operating system, it is not supporting that floating point representation also. So, as a programmer, so you can always do that, and you can use the integer formats for representing different components of the floating point number and represent it that way. So, this is known as the floating point emulation, because because the floating point number is not stored as such. So, we just create programs that so that it seems like as if we are handling floating point numbers. But most of the computers that we have today, or the processors, the advanced processors, they are equipped with specialized hardware that can do this floating point arithmetic without any special programming requirement. So, this is very important, because otherwise whenever you represent this floating point operation by means of software, the overall operation will become slower, because software is always much slower compared to the hardware. So, if the hardware directly supports the floating point format, so it is better. So, most of the processors that we have now, the advanced processors, so they support these floating point formats in the hardware itself. However, these are not embedded processors, because these are not dedicated for the floating point operation only. So, they do many other things, but they also support the floating point operation. So, how do we represent a floating point? So, floating point numbers, they allow an arbitrary number of decimal places to the right of the decimal points. For example, so floating point means so we can have any number of digits after this decimal point. So, that is the floating point. Obviously, for actual representation, so it cannot be arbitrary. So, there has to be some higher limit on the number of digits that you have after the decimal point, because a computer has got, any processor or computer, it has got a finite word size. So, you cannot go beyond that. Anyway, so if we are multiplying 0.5 by 0.25, you get 0.125. So, you see the problem, the point that this point that this bullet tells is that these numbers 0.5 and 0.25, they have one digit after decimal here and 2 digits after decimal here, and in the result I have got 3 digits after the decimal. So, after decimal how many digits will come? So, that is not fixed. So, that is why it is floating point. So, in a scientific notation, so we can represent it like this, say this 0.125 that we have got. So, it can be represented as 1.25 into 10 power minus 1. Say this 6 zeros after 5, this is a very large number. So, you can represent it as 5.0 into 10 to the power 6. So, you see that if we are representing it in this format, then the numbers, they have got two components. The first component is a number, and the second part is a power of 10. Okay. So, that way we can have different levels of the range of the numbers that we are going to store. So, it becomes larger, because we are converting it into this format. So, computers, they use this type of scientific notation for floating point representation. So, numbers written in scientific notation, they have got three components. One is the sign, another is called mantissa, another is called exponent. So, the sign is whether the number is positive or negative, that is all right. Then the mantissa part. So, mantissa will have a particular format, like in this case. So, we are assuming that we have got one digit before the decimal point. So, only one digit before the decimal point. So, this is 10 power minus 1. So, that is the exponent part. So, I need to remember this sign bit, this 1.25 and this minus 1 to know what is the number that I am going to store. So, they are called sign, mantissa, exponent representation. Computer representation of floating point numbers, so they will consist 3 fixed size field. The sign field is definitely there, so that is the sign. Then the exponent part, that is the power of 10 that we are talking about. So, the exponent part and the significant part. So, significant part is the in the previous example where when you are talking about mantissa. So, that is actually told as significant here. So, exponent is same. So, this is a very standard arrangement of this field, that is after sign the exponent will come and then the significant will come. So, depending upon the number of bits that you allocate to different portions, the sign will definitely be 1 bit, but this exponent and significant. So, you can assign different number of bits to tell like how many up to what power we can represent, or up to how many digits after decimal point. So, we can represent in the significant form. So, although the significant and mantissa they do not technically mean the same thing, so they can be used interchangeably. Okay. So, we will see why they are not same. So, the 1 bit field is the sign value that is stored here. The size of the exponent field, it is determines the range of values that can be represented, as I have already said. The size of the significant, it determines the precision of the representation. So, if I say that this significant is 32 bit, then after decimal point we are going to represent 32 up to 32 bit, we are taking the precision. So, if more number of bits are available for the significant part, so I will have better precision, and less number of bits means I will have less precision. So, that way this exponent, mantissa and significant part, so they are used. So, we will take a very simplistic example, okay, so for our discussion. So, a hypothetical simple model to explain the concepts. So, we will think that the floating point number altogether I am giving it 14 bits. Okay. So, this entire from this entire structure that I have, so that is given 14 bits. So, out of that sign will take 1 bit. So, we are left with 13 bit. Out of that 13, so exponent part we are giving 5 bits, and the significant part we are giving 8 bits. So, this is the this is our simplistic model, a 14 bit representation of floating point numbers. So, what can we do with this? The significant is always preceded by an implied binary point. So, it is, suppose I am going to represent a number say 5.5 into 5.52 into 10 power say 3. So, what we will do? So, we will not represent it like this. So, we will take it as 0.552 into 10 to the power of 4. Okay. That's why the significant is always preceded by the implied binary point. So, binary point is always at this point. So, at the very first one is the binary point. Okay. So, we do not need to store it explicitly, meaning that it starts with the binary point. So, significant always contains a fractional binary value, like here it is 0.552 as I was talking about. The exponent part, so it is a power of 2. So, instead of, since I am representing in a computer, so instead of 10 power, so I will be calling it 2 power. Okay. So, it is a power of 2. So, it is 5.52 into 2 to the power something. So, 10 to the power 3 means 1000. So, it is maybe 2 power 10 is 1024. So, it will be close to that. Okay. So, that way I can, so that the exponent part is power of 2 instead of power of 10 that we have that we are looking into. So, so suppose I am trying to represent the number 32 in decimal system into this 14 bit floating point notation that we have introduced. So, 32 is 2 to the power 5. So, in binary notation by scientific notation, so 32 will be 1.0 into 2 to the power 5. So, scientific notation means before decimal point we have got 1 digit. Okay. And in case of this floating point representation that is followed in the computer system, so we have got decimal point, it starts with the decimal point. So, this is 32 in scientific notation is 1.0 into 2 to the power 5. In our notation it is 0.1 into 2 to the power 6. Okay. So, why do we prefer the second one? So, we will see slightly later. So, this 6 Okay. So, 6 is 110. So, in the exponent part we put 110 and total 5 bits were allocated to the exponent part. Out also in this 5 bit location we stored the value 6 110, and then on the significant part. So, we have to keep only this 1 that we have. So, because this point is implied here, so I have to keep this 1, and 1 is represented like this. So, so 1 0 0 0 0 like that. So, it is 1 0 0 0 0. So, it will be 0.1 into 2 to the power 6. So, that represent again 32. So, this is, so we put 110 in the exponent part and 1 in the significant part as we have shown here. So, these are all equivalent, like say so this is the representation, they are all representing 32. So, it is 32 into 2 to the power, it is 6. So, it is 1 into 2 to the power 6. So, this is 0.01. So, this is 0.01 into 2 to the power 7. Okay. Then it is 0.001 into 2 to the power 8. So, that way this multiplying by 2 will be shifting it by 1 position in the binary representation. So, that way all these representations they have the same value, which is 32. So, they are synonymous. Okay. So, but they can also cause some confusion. So, we need to have some standardization, because otherwise what will happen is that different computers may be storing information in different format. So, as a result understanding may become confusing. Okay. So, we have to use some fixed notation. So, another problem with the system is that we have no allowance for the negative exponent. So, we have got this sign bit, but that is for the entire number. But suppose I have to represent say 2 power minus 3. So, I do not have any technique by which I can represent minus 3. So, we have no way to express this 0.5. So, that is 2 power minus 1. Why? Because this I cannot tell that my exponent part is minus 1. So, I can tell that exponent part is 1, but I cannot tell it to be minus 1, there is no sign bit. So, these problems can be fixed with no changes to our basic model. So, we can keep this exponent both positive and negative. So, how do we do this? We will see slowly. So, to resolve this problem of synonymous forms, that is for the same number we have got multiple representation. So, we have to have a rule. Okay. So, some rule has to be followed, and the rule is that the first digit of the significand must be 1 with no ones to the left of the radix point, because it is a binary representation. So, it is zeros and ones. So, I will say that my significand can never start with a 0. So, if you just look into this slide. So, you see that this representation we are telling okay, but these 3 representations we are telling that they are not correct, because my as per my convention. So, the significant part must start with a 1. So, it cannot start with a 0. Okay. So, that way we make a rule that the first digit of the significand must be 1, and to the left of it and there will be no one to the left of the radix point. So, before radix point there is no digit or no bit, but after radix point we have it always starts with a 1. So, this is called normalization. Okay. So, this process is called normalization, like say 4.5. So, 4.5 when you are representing. So, this is 1000 in 0.1 into 2 to the power 0. So, we can tell it like this. So, it can also be like 1.001 into 2 to the power 2. It can also be 0.1101 into 2 to the power 3. So, we will say that this representation is correct, because it does not have any 1 to the left of the radix point. To the left of the radix point there is only 0. Similarly, here to the left of the radix point we have 1. So, this representation is not correct, but this is correct. And in the right side, so it starts with a 1. So, in the here if you do so, it in right side it starts with a 0. So, it is not correct. So, here it is starting with a 1. Here also it starts, the right side starts with a 1, but on the left side we have got some digits. Okay. So, that is not correct. So, there should not be any digit to the left of the radix point. So, only this representation is correct in as per our convention. So, all significants must have the form 0.1 xxxx like that. So, it must start with the bit before decimal point should be 0 and after decimal point the first bit should be 1. Accordingly, we have to adjust the exponent part. Okay. So, you can adjust the exponent part and that way we can do it. So, in this model, so we use no implied bits. Okay. So, but it is 0 directly, but the implied bits we will see later. So, this is known as the process of normalization. Now, how do we go for this negative exponents? Okay. So, negative for the purpose of negative exponent. So, the technique that is used is known as biased exponent. So, a bias is a number that is approximately midway in the range of values expressible by the exponent, and we subtract the bias from the value in the exponent to determine its true value. So, we have got in our example we have got 5 bit exponent. So, 5 bit exponent means, so it can go from so if I am using negative numbers also. So, it can go from minus 16 to plus 16. So, 5 bit is all the bits may be 1. Okay. So, it maybe I so by so I may be so so it is minus 16 to plus 16. So, this out of this total in 5 bits, so I can have 32 different patterns, 32 patterns. So, 32 different exponents can be stored. So, I can make it, I can divide this range on the negative side minus 16, on the positive side say plus 16. And then what we do, we with the value we store add another 16. Okay. So, we add another 16, whatever be the result, that is actually stored. So, this is called excess 16 representation. So, so we will take an example that will make it clear. See this one says, we are again coming back to this example of 32. So, 32 representation we have seen that we are following this notation 0.1 into 2 to the power 6. So, in our previous case the significant part was storing this 1 and the exponent part was storing this 6, but we do not store 6 there. So, what we do with this 6, we add 16. So, that way it becomes 22. So, we will be storing 22 in the exponent. So, here if you look into the all possible bit pattern, so you can if you look into if you look into all possible bit patterns here, then it is all 0 to all 1. So, that means I can go from 0 to 31. So, in that range what I do, so I add 16. So, if I add 16, then this will become this 6 will become 16 plus 6 22. So, I store the pattern of 22 here, knowing that when we are calculating the value. So, this is in this is so 16 extra has been added. So, I subtract 16 from here and I will get back 6. Okay. So, if I have a negative number, so the negative can go till minus 16. So, that way that even 16 will be added to that. So, that number will become 0, the exponent will become 0. So, this way we do not have to store the negative exponents separately. So, in the following this excess notation, so this mid value will be added to the exponent and that will be stored. So, the negative numbers will also come as positive numbers only. So, in the storage, so that is known as the biased exponent concept. So, exponent has been biased by the middle of the range, so that everything becomes positive. So, next we have another example. Suppose it is 0.0625 in the binary in the decimal representation. So, this 0.0625 is 2 power minus 4, because so this is 2 power minus 4. So, in the scientific notation that we are having, so this will be represented as 1.0 into 2 power minus 4, or in our notation. So, it is as per our rule. So, it is there should be only one digit after, there should be no digit before decimal. So, this is 0.1 into 2 power minus 3. So, this is the value that we are trying to store finally in the computer, for example. Now, what we do, we take an excess 16 notation. So, with this minus 3, 16 is added. So, the value becomes 13. So, ultimately in the exponent part we store 13, okay. We do not store minus 3, but we store 13, knowing fully well that when we are looking back for the value. So, from this whatever is stored there, so I have to subtract 16. So, it was excess 16. So, 16 was added while storing it. So, while getting it back, so I have to subtract 16 and then only I can get it back, okay. So, that way I can do I can go back to 2 power minus 3, and this part, this significant part remains unaltered. So, this is known as the biased exponent concept. Another example, so suppose I am to represent the number minus 26.625 in this 14-bit representation. So, since this is minus, so the sign bit should be 1. Now, this 26.625, so if you represent it in binary notation, so it is like this, okay, 11010.101. So, we do normalization. So, after doing normalization, so it is like this. So, this is the format we want to store in the computer, but so this significant part is storing it 1101101, but for the exponent part, for the exponent part, so we take again excess 16. So, with this 5 16 will be added. So, this becomes 21. So, this 21 is stored in the exponent part. So, this way we can store the numbers in the system. So, now so this is the standard that we have developed, the model that we have, the 14-bit representation model that we were using. So, IEEE has got some standards for these floating point numbers. So, it is IEEE 754 standard, and they have got one standard for single precision number and another standard for double precision number. So, for single precision number, so it uses 8-bit exponent with a bias value of 127 and a 23-bit significand. On the other hand, this double precision number, it has got 11-bit exponent with a bias of 1023 and 52-bit significand. So, that is a very huge number. So, that way we can represent very large numbers in double precision format with higher precision values. So, both single precision and double precision use the significand has an implied 1 to the left of the radix point. So, in our model, to the left of the radix point we have only 0, but in case of this this IEEE standard, so to the left we have got a 1. For example, this 4.5 is actually this one. In our notation it will be like this, but in IEEE format, so it will be 1.001 into 10 to power 2, because that will be, so this 1 is implied. I do not need to store this one explicitly. In the storage I will only have this 001 in the significant part, but this 1 is implied. So, that means, so in our case what was happening is this 1 we were storing separately, and but that way we were actually wasting a bit, okay. So, we are wasting 1 bit of storage, but using this 1.001 to power 2, so we can so that we can save 1 bit, okay. So, that way we can have a better representation. So, this for example, this minus 3.75. So, this floating point representation, so it will be like this. So, minus 3.75 is minus 11.11. So, minus 1.111 into 2 power 1. Now, this bias is 127. So, 127 is added to 1. So, it becomes 128. Now, the sign is so negative. So, this is the sign. Now, this part is so before decimal. So, this is the exponent. So, 127. And then we have got this implied 1, and after that we have got this 111000. So, this 1 is already implied. So, this one need not be stored separately. Floating point number range for 32-bit number with 8-bit exponent and plus minus 2 power 256. So, that is about 1.5 into 10 power 77. It is a huge number. Now, accuracy, so this is the change that will come if you change the LSB of the significant part. So, if I have got 23-bit significant, then the accuracy is 2 power minus 23. So, that is 1.2 into 10 power minus 7. So, that is up. So, this turns out to be 6 places after decimal. So, that is a huge number, accuracy is good. the numbers that you can express. So, that way you can see that okay, in 2's complement range. So, it is minus 2 power 31 to plus 2 power 31 minus 1, but in floating point numbers. So, you have got a huge range. Okay. So, this is minus 1 minus 2 power minus 24 to 1 minus 2 power 24. So, that way, so that is a huge number of numbers that you can store here. Okay. So, similarly, we can have this floating point representation for this single precision floating point. So, these are this representation can be there, and this 0 this 14 bit model that we have used. So, that will also have similar such thing, but this 0 with this IEEE 754. So, this allows two representation of zeros. So, we have got minus 0 indicated by all zeros in the exponent part and the significant part, but the sign bit can be either 0 or 1. So, as a result, there is a plus 0 and a minus 0 in in our representation as well as IEEE 754 representation. So, this suggests that we should not have this floating point, we should not check whether the value is 0 or not, because of the sign bit mismatch. So, it may not be giving the correct result in a program. So, we should not try to check whether x equal to 0 where x is a floating point number, and this negative 0 does not include equal to positive 0. So, this floating point representation. So, we can do addition, subtraction, etc. So, that will be doing that we will do using similar to integer arithmetic. So, this we will see in the next class.